In this session, which I hope will be a bit quicker than the previous one, we're dealing with the same NFA, but the input string is now a little different, and we're expecting that this time the NFA will reject that string. In other words, all branches, terminating branches of that NFA will end in states that do not belong to capital F. In other words, none of those states is an accept state. Okay. Now, you do not have the state diagram, state transition diagram. And you don't have here the history, like the whole tree, the whole branching structure that we had in the previous session. So you may need to look at your textbook. I do hope you've got it. If you're following me this far, I assume you're using the text, right? So this time the input string is 0, 1, 0. Okay. So, right, so as usual, it's the same NFA, it's N1, that four-state machine. You read a 0, so Q1 goes to Q1 as before, and then you read a 1, so remember from, we did it several times, so that Q1 then splits Q1, Q2, Q3, because there's an eta there, so the Q1 in the next step goes to Q1, Q2 and Q3. Don't forget the eta arrow, that's referring to this one. Okay, and then the third symbol comes in, it's a 0. Okay, and let's see, Q3 dies because there's no exit arrow, there's no transition for a 0 from state Q3, so it dies. Okay, so Q3 dies, Q2 goes to Q3, right? And Q1 just stays in Q1 because it's reading a 0. Okay, so that's the end of the input. You've got fingers or pins on Q1 and Q3, but neither of those is an accept state, right? The only accept state for NFA is Q4. Okay, therefore the whole NFA, all those branches, they all reject. Okay, so therefore the NFA, this N1 NFA rejects the input. Now, you may ask, what is this NFA doing? What language does it recognize? So you need to do a bit of experimenting, and you can try that for yourselves as a bit of homework. I have not done it, but the conclusion is, with more experimenting, input various strings and see what happens. Then you'll find that N1 accepts strings that have substrings, somewhere in the string. Remember, a substring is a sequence of symbols contiguous, right? It's not as though here's your string, and say you cut out a snippet here and a snippet there, and then joined them together or something. That is not a substring. A substring is you cut out one snippet, and they're all contiguous. So they're all next to each other, all neighbours, sort of thing. You're not like taking two substrings and making them one substring, right? Okay, so this language are all those strings that have as substrings two possibilities: either 101 or 11. Now, not obvious, right? Okay, so that's the language of that N1 non-deterministic finite automaton NFA. All right. Okay. Double line. That usually means a bit of a change of topic, somewhat. So now we're going to talk about put asterisks here, what, 3 of them? And then I'll get on to another example, a different example of an NFA. You may be asking, well, what's the point of these NFAs? You know, why are they introduced? How are they useful? How do they help things? Well, there's three different answers. They're well, obviously they're very useful because there's pages and pages of it in the text, and in chapter 1, right? So really basic. Okay, so here's one answer to that question. You know, why NFAs? What's the point? Well, we'll show soon, a couple of boards from now, I think, that for every, and I mentioned this in the previous session, for every NFA you can construct, you can design, build an equivalent, meaning doing the same job, in other words recognizing the same language. For every NFA there is an equivalent DFA. Right? For every non-deterministic finite automaton there is an equivalent deterministic finite automaton. You're doing the same thing, performing the same task. Right? And so what? What's the point of that? Well, sometimes it's easier and quicker to take an indirect route to designing something. So you have some task, right? You're asked to find an automaton that recognizes a certain language, you know, certain kinds of strings. You know, each of these strings has something in common. And one way would be just to find the DFA directly, you know, a direct approach, and that may end up being more work than a more indirect, like two-step approach, where you first design an NFA, right? And then from the NFA you find the equivalent DFA. Now that second approach, even though it's two-step, it may end up being more less work, you know, less effort, easier to understand, easier to do than the one-step direct design of a DFA. Okay, so you know, important consideration. So that's one reason why NFAs are useful and interesting. Now this one's a big one. And you'll see, like next session, you'll get a clear example of what the point that's being made here, and that is an NFA, you know, non-deterministic finite automaton, can actually be a lot smaller than its equivalent DFA, meaning less states, less complicated, right? So an NFA can be just, you know, much smaller, easier to understand than the equivalent DFA. And another one here, the NFAs with the I put 2 little bars under here, 2 little wiggles to emphasize the F, finite. So thinking about non-deterministic finite automata, yeah, plural. It's a good introduction to non-determinism because they're finite, they're easier to understand. Now later in the text we will get into more powerful computational models than just finite automata. You know, we will get into, well, Turing machines and stuff like that, which are different. They use a different model of computation. For a start, well, they're not finite. They can be infinite. And using NFAs with the emphasis on the finite is a good lead-in towards these later, more powerful models of computation. So you can look on NFAs as a kind of stepping stone for understanding towards these more complicated, more powerful alternative models to how to compute, models of computation. Right? So there's a third reason. Okay? So and the reason why they're a good stepping stone, NFAs, is because they're finite automata. and easier to understand. Right. Now another example. So this is example 1.30, 1.30. As always, I use the same IDs as in the text, right? So you can find where this is in the textbook. Now the language